Assalamualaikum students. Today's topic is going to be about work and energy, and we also try to do efficiency and work. First of all, we have a topic about work. So what is work? In physics, work is said to be done when a force acts on a body and moves it in the direction of the force. The question arises how much work is done. Naturally, greater is the force acting on a body and longer is the distance moved by it. The larger would be the work done. Mathematically, work is a product of force and displacement S in the direction of the force. Thus, the work done is equal to force into displacement. Now, here we have a box and we are applying some force on it. It will travel a distance of S. Here we go, like this. That means some work was done on it when some force was applied on it. So the work can be defined as work is done when the force is acting on a body displaces it in the direction of a force. Work is a scalar quantity. It depends upon the force acting on a body, displacement of a body, and angle between them. Now, in the first case, there was no angle. Now, let us assume that if there was an angle, now what will happen? Sometimes the force displacement do not have the same direction as shown in figure. Let me show you the figure in, let's say, 6.2. Here the force is making an angle theta with the surface of the box, which can be seen right over here. Now here's a box and here's the force, and we can resolve that force into its two components, one along the x-axis, the other one along the y-axis. Now as you can see, here's the angle theta, and the forces are being differentiated, or you can say broken down into two components. One is which is along the y-axis, that is by Fy sine theta, and one is along the x-axis, which is Fx cos theta. Now students, the bodies move and resolve into its perpendicular components. One is Fx cos theta and the other one is Fx sine theta. Let's move this body now. Again, this body has moved from one place to another, covering a distance or displacement, in this case, of S. In case when force and displacement are not parallel, then only x component Fx, which is parallel, is taken to the surface, causes the body to move on the surface, and the y component Fx is not taken. Hence, W is equal to Fx into S, which will have a component value which is taken from here. So W, that means work done, will be equal to F cos theta into S. So we can simply write it down as W is equal to Fs cos theta. Moving on to our unit of work, the amount of work done or amount of work is 1 joule when a force of 1 Newton displaces a body through 1 meter in the direction of the force. Thus, joule is a small unit of work. Its bigger units are 1 kilojoule, which is 1000 joule, or we can say 10 to the power 3 joules. Now this thing can be represented also as megajoules. 1 megajoule is equal to mj is equal to 100,000 joule, or we can say simply 10 to the power 6 joule. Energy. The energy is an important fundamental concept in science. That means we can't do anything without it. It links almost all the natural phenomena which we say that a body has energy. We mean that it has ability to do work. Water running down the stream has ability to do work, so it possesses energy. That means if there is a height and the water is flowing down from that height, then we say that that water, that even non-living thing, has some energy. The energy of running water can be used to run water mills or water turbines. Energy exists in various forms such as mechanical energy, heat energy, light energy, sound energy, electrical energy, chemical energy, and nuclear energy, etc. Energy can be transformed from one form to another. Yes, energy can be converted from, let's say, heat energy into electrical energy. Now, in many cases, we can do the uh, transformation of energies, just like mechanical energy possesses by a body, if which are of two types. One is kinetic energy and the other one is potential energy. Now, potential energy can be converted into kinetic energy, and kinetic energy can be converted into potential energy as well. But we have to understand what is kinetic energy. Moving air is called wind. We can use or wind energy to for doing work for various things. It drives windmills, pushes sailboats. Similarly, moving water in a river can carry wooden logs through the large distances and can also be used to drive turbines for generating electricity. As you can see over here, the wind is blowing in this case and pushing this ship in a certain direction. Similarly, this water is falling down through certain rocks and it is carrying some um, materials with it, such as log, etc. Thus, moving bodies such as kinetic energy causes or because it can do work used due to motion. So we can say energy due to motion is known as kinetic energy. The body stops moving as soon as all of its kinetic energy is used up. Now let us assume with this example, we have a ball. As the ball is falling down, it has kinetic energy, but as soon as it stops moving, so the kinetic energy vanishes, and all of that energy is converted into heat energy between the floor and the molecules of that floor, and the sound you can say. Now let us drive the kinetic energy. What is the formula for that kinetic energy? Consider a body of mass m moving with velocity v. The body stops after moving through some distance s due to some opposing force such as force of friction acting on it. The body possesses kinetic energy and is capable of doing work against the opposing force F until all of its kinetic energy is stopped. Let's assume this is the mass and it moves and suddenly stops. Now, as it stops, when it was moving, it had the kinetic energy. So we'll say the kinetic energy of the body is equal to the work done because it has displaced some distance when it has some force. So we can say the work is to be done or work has been done in this case. So from the formula of work, we can say the kinetic energy is equal to Fs, but that is not enough. Let us define the mathematical formula with the help of an equation. So we have the initial velocity, which was Vi, which was over here, and the final velocity, which it has, which is equal to 0, because it stopped. And as the body was moving from here to here, its acceleration was decreasing. So the negative acceleration, that means the Vf is less than Vi in a certain amount of time. So if Vf is 0, then only thing which is left, which is Vi, so there's a negative sign over here. So that is why we are taking acceleration is equal to minus F over m through second law of Newton's second law, which said when a force is applied on a body, the body moves in the direction of the force with some acceleration. Now, we can use this acceleration in a certain kind of equation of motion. Since motion is opposed, hence A is negative. That means in opposite direction. Using the third equation of motion, so we can see from here, which said 2as is equal to vf square minus vi square. So vf is 0 in this case. So if the body was over here and it moved down till here when vf was 0, so from this equation, we are driving the formula for kinetic energy. So 2as, which is the distance, is equal to Vf, which is the final velocity square, minus Vi, which is the initial velocity square. Putting in the values, what do we get? 2as is equal to 0 square because Vf was 0, and Vi was equal to some velocity v. Let's consider that. So in this case, we said that 2as is equal to Vf square minus. That means initial velocity is in minus. Now, in this case, we have to find the force in this case. Here we have A is equal to minus F over M. Where did that come from? It was written over here. As we know, A is equal to minus F over M. So using this in this formula, we can say that 2A, instead of A, we can say F over M into S is equal to minus Vi square. Or we can say V square, no problem with that. So let us remove this one. Moving on to our derivation. So this negative sign and this negative sign cancels out. This m goes to the other side and this 2 goes to the other side. So it will be Fs is equal to 1 over 2 mv square. So that is why I have written Fs is equal to half mv square. And in this way, we have figured out that this formula and this formula, let's call this equation number 1 and equation number 2. If we compare these two equations, from equation 1 and equation 2, we get kinetic energy is equal to half mv square. So the value of kinetic energy mathematically, we have found it as to be half mv square. Equation gives the kinetic energy possessed by a body of m moving with a velocity v. Potential energy. Now we'll discuss the second type of mechanical energy. Often a body has ability to do work through it is at rest. For example, an apple on a tree capable of doing work as it falls. Thus, it possesses energy due to motion. Now, if we assume that this is a tree and there's an apple on it, so when it falls, it has some height. That height would helping it to gain some energy. If it falls and is present at the ground, it has no energy because it has position at the ground level. So it will not have a potential then. Now, the kind of energy which a body possesses due to its position, and remember, position must be at a certain height or certain distance, is called its potential energy. Stored water possesses potential energy due to its height. A hammer raised up to some height has ability to work because it possesses potential energy. A stretched bow has a potential energy due to its stretched, or you can say extended position. When it is released, the stored energy of the bow pushes the arrow out of it. The energy present in the stretched bow is elastic potential energy. Now, in all of these cases, it has some potential due to its position. Potential energy possessed by a hammer is due to the height. The energy present in its body due to the height is called gravitational potential energy. Now, here are the two cases. As there is a height between the hammer and the nail, so it has potential. And this extension of this wire, so let's call it X. So more the extension, more the potential of this arrow to go far away. And if it has a certain height, let's say if we have a ball standing on or top of a table, then it also has some height, and it has a height, so it has also a potential over here. Let a body of mass m be raised through a high h from the ground. The body acquires a potential energy equal to work done in lifting it through high h. That means if we pick up a ball and place it over a high h, that means it must have some potential now. But in this whole case, force was applied on this ball and it basically covered a distance of h. So in this case, we can say that work has been done on it. So the more the work done on a body, more the potential it has. Such potential energy is equal to F into H. Here we can say the force is the work done and H is the height. Here we have the, or we can say in this case simply, the force can be represented as the weight of that body because W is equal to mg and weight is a force and there is a height also where it basically moved from one place to another. Here we have the weight of the body which is equal to mg and potential energy will be equal to the weight into height, so mgh, and this is the formula for potential energy. Thus, the potential energy possesses a body with respect to the ground is mgh is equal to the work done. Now, this line is very interesting. The more the work done, more will be its potential. That means in this case, the work done is equal to mgh. Now, over here, don't be confused by this w. This w is not representing the weight, it is representing work in this case. If we say the work done is equal to mgh, then this mg is the weight and this h is representing the height. So we'll represent mg as small w and the work done by capital W. Efficiency and power. Let's define efficiency first. How to get work done from a machine. We provide some of the energy to a machine. This is necessary for the machine to work. Human machine also need an energy to do variety of work. We take food, fulfill our energy needs of our body. That means in this paragraph that everything does work with a certain capability. Somebody does a better work than the other, and that comparison will be defined over here. We give some form of energy or machine as input to get useful work done by them as output. For example, electric motors may be used to pump water, to blow air, to wash clothes, to dry clothes, to drill holes, and etc. For that depends how much output we obtain from it. Giving certain input, the ratio useful output to the input energy is very important. That means this line, the ratio of useful output and to the input is very important. That means how much is we are giving to the system and how much system is giving back to us. So important to judge the working of the machine. It is called the efficiency of that machine and it is defined as efficiency of a machine is the ratio required form of energy obtained from a system as output of the total energy given by it as input. That means output will be on the top and we are taking a formula and the input will be at the denominator so that we can compare how much output we are getting and how much input we are giving. So efficiency can be defined mathematically as efficiency is equal to required form of output energy to the total input energy. Or if we want to calculate that into percentage, so what do we do? So percentage efficiency is equal to required form of output divided by total input energy multiplied by 100. An ideal system is that which gives out equal to total energy used by it. In other words, efficiency is 100%. That means an ideal system input will be equal to output. But students, none of our machines in this world works in certain manner. Every machine has output less than its input, which is basically the second law of thermodynamics, but we will discuss that later. But practically such a system does not exist. Every system meets energy losses due to friction that causes heat, noise, etc. These are not the useful form of energy and go to waste. This means we cannot utilize all the energy given to a working system. That means we can't convert every input into its output. Some of the energy has to be lost due to heat and friction. The energy is in the required form obtained from working system is always less than the energy given to the it as input. Now that sentence basically summarizes it all, that whenever we give some input to a system, we are expecting that we'll not get the output as we have given it the input. Now let us discuss power. For that, two persons have done equal work. One took 1 hour to complete it and the other completed in 5 hours. Now, who is much more powerful, the one who does it in small amount of time or in larger amount of time? Yes, no doubt, both of them have done the same work, but they're different in rate at which the work is done. The one has done faster than the other. Similarly, the second one has done the work but in lot of time. So the quantity tells us that the rate of doing work is called power. That means the person who does the work in less amount of time has more power. Power is defined as rate of doing work. Here the rate is the main keyword over here, because the rate defines the time in which the work has to be done. Mathematically, power is equal to work done divided by time taken, or we can say mathematically P is equal to W over T. Since work is a scalar quantity, therefore power is also a scalar quantity. SI unit of power is watt. It is defined as power of a body is 1 watt if it does work at the rate of 1 joule per second, or 1 J over S. Bigger units of power are 1 kilowatts or 1 megawatts, just like in the case of work. So 1 kilowatt is equal to 1000 watt or 10 to the power 3 watts. 1 m watt or 1 megawatt is equal to 10 to the power 6 watts. 1 horsepower is equal to 1 HP, or 1 HP we can say is equal to 746 watts, where HP is representing horsepower. Horsepower is another unit in olden days of measuring power. I hope you liked today's topics. Inshallah, we'll meet again. Allah Hafiz.